I'm going to introduce the basics of stoichiometry, and then we're going to do some stoichiometry examples. So stoichiometry is just relating amounts of substances in a chemical reaction. So relating the quantities of reactants to products or reactants to reactants and so on, to figure out how much of something would be produced or how much of a reactant you need. And so let's talk about kind of how we go about doing these quantifications. Now, the first thing is you need a balanced chemical equation. Okay, and so the balanced chemical equation is essentially your recipe. Okay, it's your recipe for the chemical reaction. And the coefficients in the balanced chemical equation represent the number of atoms or the number of molecules that you need to do this reaction and how much stuff you would get from this reaction. Okay, so it's all of the coefficients. If there's not a coefficient, remember that is a 1. You can also use the coefficients to represent number of moles instead of talking in terms of individual atoms and individual molecules. That is the most common that we do because we don't normally work on the scale of atoms and molecules. We work on the scale of moles of atoms or moles of molecules. So normally when we talk about a reaction, we'll use those coefficients to talk about how many moles of things are needed or are produced from a reaction. So for instance, if we have this reaction with iron and oxygen reacting, forming iron 3 oxide, this is a balanced chemical equation. So I've already got the stoichiometric coefficients that are telling me how much stuff I need and how much I'm going to produce. And so the 4, the 3, and the 2, those are going to help us do stoichiometry. So that's why instead of just calling it a coefficient, a lot of times we'll call it a stoichiometric coefficient. And so those numbers you can either relate to atoms or molecules or moles of atoms and molecules. So I could look at that reaction and say that 4 iron atoms are going to react with 3 oxygen molecules to produce 2 formula units of iron 3 oxide. Okay, or I could say that 4 moles of iron will react with 3 moles of oxygen to form 2 moles of iron 3 oxide. So either way is correct. And so that's our recipe. It's telling us how much of the reactants we need and how much of the product we're going to get. But just like a recipe, you can scale that up and down. And so that's what essentially we're doing with stoichiometry. We're kind of scaling things to what we are actually using in our reaction. But we're basing it on that balanced chemical equation. So let's talk about stoichiometry just a little bit more before we do examples. So it's using the relationships or the numerical relationships between our chemical substances in a balanced chemical equation. So here's another balanced chemical equation. Okay, so another recipe telling me how much of stuff I need to produce a certain thing. And so in this case, we've got a combustion reaction between propane and oxygen gas, forming carbon dioxide and water. And it tells me that for every 1 propane molecule, I'm going to need 5 oxygen molecules. Or for every 1 mole of propane, I need 5 moles of oxygen. And that it produces 3 molecules of CO2 and 1 molecule of H2O, if I'm talking on a molecular level, or 3 moles of CO2 and 1 mole of water, if I'm talking on the mole level. And so that information we can utilize to quantify things for the actual scale of the reaction that we want to do. Okay, so we might not want to react just 1 molecule of propane or just 1 mole of propane. Maybe we want to react 5 moles of propane, or maybe we want to react 1.23 moles of propane. And so we want to be able to scale then everything else to the amount we're actually going to use. Okay, and quantify how much of the other reactant do we need, how much product can we form, and so on. So to do that, what we do is we create mole ratios from the balanced chemical equation. Okay, now most reactions you can create, I'd say at least probably 8 or more mole ratios. This one, I think we've got quite a bit more than that. I think we've got even 12 different ratios that we can create. And you create the ratio based on what you're trying to convert. Okay, so what you know information about and what you're trying to get to. Okay, so we can start with an amount of reactant and we can quantify, say, how much of the other reactant is needed. Okay, so let's say I have a particular amount of propane or C3H8 that I want to react, and I want to calculate how much oxygen gas am I going to need. So if I wanted to do that, I'd use that first ratio written because I'd start with the moles of propane, and then I can multiply by that ratio of 5 moles of oxygen over 1 mole of propane, and then that would tell me how much oxygen I need. Or other way around, I could start with some amount of oxygen and convert it to moles of propane by using that second ratio. So those ratios came from the balanced chemical equation. Okay, it comes from just the stoichiometric coefficients. And so the propane doesn't have a coefficient, meaning it's a 1. And then the oxygen has a 5. And so notice in those ratios, I put a 5 in front of moles of oxygen and a 1 in front of moles of propane. Okay, and so those come from the balanced chemical equation. So you absolutely have to have a balanced chemical equation in order to do stoichiometry, because that's how you're going to build your mole ratios. Okay, so that's one thing we can do. We can quantify how much of one reactant we're going to need in order to react the other. Okay, we could also convert a reactant amount to a product amount, meaning if I know I'm reacting a certain amount of propane, I can calculate how much CO2 that will produce or how much water that will produce. Okay, by setting up ratios that relate propane to CO2 and propane to water. Okay, I can do the same thing. If I had a starting amount of oxygen, I could calculate how much product I would get. Okay, set up ratios for CO2 and H2O from oxygen. Sorry. So I have all 4 of those ratios there. And what you'll see is anytime you see propane in those ratios, it's listed as 1 mole. Okay, because in the balanced chemical equation, we have 1 of those. And anytime you see O2, there's a 5 there. It's 5 moles because that's what's in the balanced chemical equation. And anytime you see moles of CO2, it's 3 moles because that's what's in the balanced chemical equation. And then it's 1 for the H2O because that one doesn't have a coefficient, or it really has a coefficient of 1. So all of those ratios could be used to convert from a certain amount of reactant to how much product. Okay, so if we knew how much we were starting with, we could quantify how much product am I going to get from this. Okay, we could also reverse that process. We can take some amount of product and figure out how much reactant we need. So that's a pretty common scenario. A lot of times we're doing this reaction because we want a certain amount of product. And so we can start with what our goal is, what we're trying to get, and we can convert that product back to reactant to quantify how much reactant do I need to start with to get my goal. Okay, and so I've got another 4 ratios there, converting the CO2 to C3H8 and to the O2, and same with the water. Okay, and so all of those are just inverse of the ratios that I had for reactant to product because we're just reversing the process. Okay, and then lastly, we could also go from a product to another product, meaning if we knew how much of one product was formed by this reaction, we could calculate how much of the other reactant must have been formed as well by converting the amount of the one that we know to the amount of the one we don't know. Okay, and so then I have two more ratios there. So we've got 12 ratios just for this reaction alone. And every reaction has its own mole to mole ratios. And those aren't given, but typically you're given a chemical reaction, may or may not be balanced. You have to be able to balance them. But once you have a balanced chemical equation, you should be able to create all of these ratios. But normally we don't just write them all down. Normally we have some goal in mind. So we're trying to do some particular calculation and we'll build the ratio we need when we need it. Okay. And the way we figure out what ratio we need is by performing dimensional analysis. Okay. And so you follow the units and it'll tell you what mole to mole ratio you need. Okay. So with stoichiometry, it's all based on mole to mole ratios that come from a balanced chemical equation. And so you can convert from moles of one thing to moles of another, meaning that you're going to need to know moles of something in that reaction in order to calculate the other things. Now, a lot of times we don't measure things in moles. A lot of times we measure like masses of our samples. But you can convert masses to moles using molar mass. And so sometimes you have to do multiple steps to do your stoichiometry calculation. But one step that's always there is using a mole to mole ratio. So you always have to, you don't start with moles, go to moles first. Okay, so convert whatever you have to moles. Once you have that, you do your true stoichiometry step where you pull a mole to mole ratio from the reaction. Once you do that, then you may need to convert the result into whatever unit you're looking for. Okay, because a lot of times we don't report it in moles, we report it in something like grams. And so we're going to go through some examples of using stoichiometry. So this first one, I say, according to the following balanced equation, how many moles of nitrogen gas are necessary to fully react with 9.0 moles of hydrogen gas? Okay. So we only have one value to start with, so I'm just going to go ahead and write down that value because I have to start there. And so I have 9.0 moles, so MOL, of H2. And when you're doing stoichiometry, you definitely want both the unit and the substance. So you should kind of be writing three things down: a number, a unit, and a substance identity. Okay. And that all is important in the calculation. Okay. You need the numbers or you can't calculate anything. You need the units with the substance so that the dimensional analysis can lead the way. Okay. So we have units of moles already. So I don't need to convert to moles. I'm already there. And so I just want to focus on, well, I don't want moles of H2. So I'm going to put it opposite. So this is, essentially this value over 1, right? So I put moles of H2 opposite, and then I want moles of nitrogen gas. So I want moles N2. So I would put that in my empty spot. And then I'm going to fill in numbers. This is a mole to mole ratio. Okay, I have moles on top, I have moles on bottom. I get that information from my balanced equation. So from my balanced equation, N2 has no coefficient written, meaning it's a 1. So I put a 1 there. And then H2 has a stoichiometric coefficient of 3, so I put a 3 there. And so my moles of H2 is going to cancel, and that's going to tell me how many moles of nitrogen gas I would need to fully react with 9 moles of hydrogen gas. And so that gives me 3.0 moles of N2. Okay, it's 2 sig figs because our starting value is 2 sig figs. The mole to mole ratio is exact, so that doesn't limit it. And so that is my answer. Now, if you stop and just think about this and look at the reaction, that answer should make sense. They react in a 1-to-3 ratio. So you only need a third as much of nitrogen, okay? So sometimes you can reason out stoichiometry in your head, but I would recommend that you get in the habit of writing it out as dimensional analysis, because this one I gave you some nice numbers you could work with in your head. It makes sense, but most of the time the numbers we're working with, the moles don't come out to this pretty whole number that just happens to factor properly into the stoichiometry. And so you've got to get used to this process. So that's our answer, 3.0 moles of nitrogen gas. Now let's do another one with the same reaction. So here, I want to know how many moles of ammonia can be produced from the complete reaction of 9.0 moles of hydrogen gas. Okay, so we're working with the same reaction, the same amount of hydrogen gas. I quantified how much nitrogen I would need to do this reaction. Okay, but now I want to know how much product I'm actually going to get from this. And so I'll start with the only value given here, so the 9.0 moles of hydrogen gas. And again, focus on the units, okay? You really should focus on the units first. So the moles of H2, I'll put opposite, I'll put it on the bottom since it starts on top. And then I want moles of NH3, so I'll put that in my open spot. And then I can fill in the numbers by looking at the reaction. So NH3 has a stoichiometric coefficient of 2, and H2 has a stoichiometric coefficient of 3. Okay, so if you go through and calculate that, the moles of H2 are going to cancel. You're going to have 9 times 2, which is 18, divided by 3, which is 6, and it should be rounded to 2 sig figs, so it's 6.0 moles of NH3 is how much product I would get. Okay, again, I gave you kind of nice numbers here where you could do it in your head or reason it out, but follow this setup by taking some moles, or if you don't have moles, convert it to moles, and then follow the units and let the units tell you what ratio to multiply by, because when you're starting to work with more realistic numbers, sometimes if you're trying to do it in your head, you're just going to get things wrong. Okay, so write it out, let the units tell you what to do. Make your life a little bit easier. Don't memorize this stuff. Okay, now got a new reaction, and I say what mass of oxygen gas is required to completely react with 12.5 grams of tetraphosphorus hexoxide. Okay, so again, I'm only given one value, so I'm going to have to start my calculation there. So I've got 12.5 grams of P4O6, okay, and I want to know how much oxygen gas is required. So I'm going to need to convert from P4O6 to oxygen gas, which both of those are in that chemical equation, okay? And so if I can get to moles, I could do a mole-to-mole ratio to jump from one thing to the other. So first step is get to moles if you're not already in moles. So I need to get rid of grams of P4O6, and I need to go to moles of P4O6, okay? And so that, a gram to mole relationship you get from the periodic table. And so we take 4 times phosphorus's molar mass, so 30.97 grams per mole. And then we take 6 times oxygen, so 16.00 grams per mole to get our molar mass. So 4 times 30.97 plus 6 times 16.00. And it looks like that gives me 219.88 grams per mole. And so that goes in as the grams, 219.88 0.88 grams per 1 mole. That's going to cancel my grams of P4O6. So now I have moles. And so that means I can convert from one substance to another. So I would put moles of P4O6 on bottom, so it'll cancel, and moles of what I want on top, which in this case is oxygen gas, so O2. And now I need my mole to mole ratio. So I look at the balanced chemical equation. But if you look at this equation and you say, okay, well, here's O2, and there's one of those, and here's P4O6, and there's one of those, you should be a little suspicious because it's pretty rare that we have things, at least, you know, in kind of general chemistry, that react one-to-one. Okay, a lot of reactions don't react one-to-one. Maybe when you get into organic chemistry, they do. But in here, it doesn't. And so you might question, you know, looking at that reaction, that there's no stoichiometric coefficients. You might question, is it actually balanced? Okay. I gave you a reaction, it doesn't mean it's balanced. If there's coefficients, it's balanced because we don't write things down half balanced. Okay. But if you look at this, we've got 4 phosphorus on both sides, but at the moment we only have 8 oxygens on the left and 10 on the right. So it is not balanced. And so what we need to do to balance this is put a 2 on the oxygen. It's not the best 2. Try that again. And so we have a 2 in front of the O2 now. Now it's a balanced reaction. So now I can fill in my mole to mole ratio. So a 2 with the O2 and a 1 with the P4O6. Okay, so that's going to cancel my moles of P4O6. And then I want mass of oxygen. So I want to convert my moles of oxygen to grams of oxygen. Okay, so you need the molar mass. When you look up oxygen, 16.00, and you have 2 of those in there, so that's 32.00, right? O2 is 2 atoms of oxygen. So double the individual oxygen mass. It's 32.00 grams per mole. Okay, and that's going to cancel my moles of O2. So now I just need to type all that in the calculator. So I've got 12.5. I divide it by 219.88, and then multiply by 2, multiply by 32. And that gives me 3.64 grams of O2. And I rounded it to 3 sig figs because the fewest I have in my calculation is from the 12.5 grams, which is 3 sig figs. Okay, so that's how much of the oxygen gas I would need to completely react my 12.5 grams of P4O6. Now, let's do another one. So we're going to use this same reaction. So it'd probably be helpful if I carry my balancing. This should be a 2. And I want to know what mass of P4O6 is needed to produce 3.75 grams of P4O10. Okay, and so now I have an amount of product and I want to know how much reactant I need. Okay, and it really doesn't matter where you're starting in the chemical equation. Okay, whether you're starting with reactants or products, it doesn't matter. It's always the same process. Convert what you have to moles. Once you have moles, set up a mole to mole ratio, and then convert to whatever units you want. So in this case, we start with the 3.75 grams of P4O10, because that's what we were given, and we need to get it to moles. Okay, so I'm going to put grams P4O10 on the bottom, and I'm going to put moles of P4O10 on top. And so I need to add up that molar mass. So whatever 4 times 30.97 grams per mole plus 10 times 16.00 grams per mole. Whatever that is, that's my molar mass, which, let's see, that gives me 283, oops, 283.88 grams per mole. Okay, so that goes here, 283.88 grams per 1 mole. So that's going to cancel my grams of P4O10, and now I can do a mole-to-mole ratio. So now I can convert moles of P4O10 to moles of P4O6 because that's what I want. Okay, and you look at the reaction, and P4O10 is 1 mole, and P4O6 is 1 mole, right? And that is balanced because we already balanced that reaction on the previous example. So you can have 1-to-1 mole ratios, but if you look at your reaction and there's no coefficients, just double check and make sure it's balanced, okay? And we did that already. So our moles of P4O10 cancel, and we want the mass of P4O6. So we want to convert moles of P4O6 to grams of P4O6, which we added up on the last example, and it was, I believe, 219.88 grams per mole. So that will cancel our moles of P4O6 and give us grams. So we need to calculate the answer by taking 3.75, divide by 283.88, multiply by 1, and multiply by 219.88. Okay, so the answer comes out to 2.90 grams of P4O6, again rounded to 3 sig figs because the 3.75 is my fewest sig figs in this, and it's 3. Okay, now let's do a few more. So this problem, we've got dihydrogen sulfide gas and sulfur dioxide gas reacting to form solid sulfur, so S8, and water. Okay, so I've got the balanced chemical reaction there already. Really, in the title there, I gave you enough information that you should be able to write the reaction yourself and balance it yourself, but I went ahead and gave that this time. So I've got a couple questions for this one. And we're going to first calculate how many grams of sulfur dioxide would be needed to react with excess dihydrogen sulfide to form 20 grams of sulfur solid. Okay, so this one, we're given only one value. So again, we can start there. So 20.0 grams of solid sulfur, okay, which is S8, right? And so we have that to start with, and we want to know how many grams of sulfur dioxide is needed, okay? They also say that there's excess of that H2S, okay? Just saying that we have plenty of it. So sometimes they don't tell you that. Most of the time, if we don't tell you something about one of the reactants, you assume that there's enough, okay? It must be present, otherwise we wouldn't be asking the question, okay? So we're trying to convert to SO2. We have grams of S8. We have to get it in moles first. That is always the first step. And so we want to convert moles of S8, or sorry, grams of S8 to moles of S8, okay? And so we need to take sulfur's molar mass, which should be 32.07 times 8. And so the molar mass of S8 would be 256.56. Oops. Oh, grams per 1 mole. So that's going to cancel my grams. That gives me moles. Now I can convert from moles of what I have, so moles of the S8, to moles of what I want to know about, which would be the SO2. Okay, so I look at the reaction, and SO2 has a coefficient of 8, and S8 has a coefficient of 3. So that's going to cancel my moles of S8, give me moles of SO2, and we want grams of SO2. So that we put moles of SO2 on the bottom, grams of SO2 on the top, and we need to add that up. So you take the mass of one sulfur, which would be 32.07 grams per mole, and add it to 2 times oxygen, so 2 times 16.00, and that gives you the overall molar mass, which is 64.07 grams per mole. And now we can put all of that together. We take 20 and divide by 256.56. 56.56, and then multiply by 8, and divide by 3, and multiply by 64.07. So it looks like we have an answer of 13.3 grams of SO2. And I did round that again to 3 sig figs because the given value limits us to 3 sig figs. Okay, now the next one, this is a little different than the others, but it's still a stoichiometry problem. Okay, this one I'm asking for how many milliliters of water will be collected when 55.5 grams of the H2S reacts with excess sulfur dioxide. Okay, so this time we have plenty of SO2, we have a given amount of H2S, and I want to know how much water. Specifically, I want to know how many milliliters. So really, I'm looking for a volume, okay? And so far, what we've been doing is calculating moles and calculating grams. But if you can get grams, that's mass, you should be able to convert it to a volume, specifically milliliters, using the density, okay, which was given as well. So we give you the density of water as 1.00 grams per mil. So let's start this with the given amount of reactant. So this 55.5 grams of H2S, okay? So that I need to convert to moles in order to be able to convert between substances using the balanced chemical equation. So I'm going to get rid of my grams of H2S. I'm going to convert it to moles of H2S by using the molar mass. So I'm going to add up 2 times hydrogen's molar mass, so 2 times 1.01, plus sulfur, which is 32.07, and that gives me 34.09 grams per 1 mole. Okay, so that cancels my grams and gives me moles, which is supposed to be a 1 there. Oh, and now I can go from moles of H2S to moles of what I am looking for, which in this case is water. Okay, trying to figure out information about water. So then you look at the balanced chemical equation. You have 16 for water, and then H2S, you also have 16. So it's a 16 to 16 mole ratio. You could, if you wanted to, write it as 1 to 1. Okay, either is okay here. I'll leave it 16 to 16 because that's your true mole ratio from that balanced chemical equation. Now, that cancels the moles of H2S. We have moles of H2O, but that's not what I want. I really want that volume in milliliters, but I can't convert directly from moles to milliliters for this water because I have the density. And in order to use density to get to volume, I need mass first. So that's what I'm going to go to, is mass. And so if you add up the molar mass of water, you should get 18.02 grams per mole. That will cancel our moles of H2O. And then we have grams of H2O. And we want to go to milliliters, H2O. We can do that using the density, which is given as 1.00 grams per milliliter. So we would take 55 we divide by 34.09. You can multiply by 16 if you want, but you need to divide by 16, so it's going to end up canceling out. And then you multiply by 18.02, and then you can multiply and divide by 1 all you want, and it won't change it, but then we get our answer, and that comes out to 29.1 milliliters. Because my density is 3 sig figs and my starting mass was 3 sig figs. So that's my fewest in the calculation. Okay, so that's the basic idea of how you do stoichiometry. The key is you absolutely have to have a balanced chemical equation. And once you have a balanced chemical equation, you want to convert whatever information you know to moles. And then you could take those moles and convert them to moles of whatever you're looking for information about by using a mole to mole ratio you build from the chemical equation, okay, from the balanced chemical equation. And then you may need to do some more unit conversions, okay? So that's the basic idea of stoichiometry.